welcome back. So in this video we're going to be talking a little bit about how to take data, and this may be a little bit of review for you, which is fine, or there might be some new things that you pick up. So I want to start with a picture of our stop clock from the lab and talk a little bit about how to take data and how to estimate uncertainties and precision and accuracy. And it's not the most exciting topic, but it's very important. So we talked about this in class, but you want to always try to estimate one digit. So for example, on this stop clock you can see that it's measuring in 1/100th of a second. Okay, so that means that this 10 right here actually is 0.10 seconds. But we don't want to leave our measurement at 0.10. We can see that the needle is actually a little bit beyond 0.10. So it's not quite halfway to 0.11, which is this tick right here, and this is 0.12, 0.13, 0.14. Okay, it's not quite halfway, so what I might do is I might estimate it as 0.10, let's say 3 seconds. So that's the way that we will estimate, and we'll put a little mark over that 3 to show that that's the uncertain digit. We're not going to do that all year, but we'll start it that way. So now let's talk a little bit about accuracy and precision. Okay, so accuracy could be thought of how close we are to an accepted value. For example, let's say that you take a quarter, and a quarter has a mass of 5.670 grams. So this is the mass of a quarter. I looked it up on Wikipedia. And let's say that you have a balance in your class, or an electronic scale or whatever, and you toss a quarter on it and it comes out to let's say you measure the mass is 5.720 grams. Well, that's pretty good. That's pretty close to the accepted value. And we could talk about how far away it is. It's 0.05 away. Okay? Or we could talk about the percentage it is away from the accepted value. And the percentage would be the amount of error divided by the actual accepted. And we can talk about that a little bit later, but you can see that this is a pretty small number. Okay. The other thing that we could talk about is the precision of a measurement. And the precision is how close repeated measurements are to each other. So let's take that same example of a quarter and we toss it on a scale in the classroom. Let's say we have 3 separate scales sitting in different places, and one of them says, I'm just going to make this up, 8.673 grams, and the next one is 8.672 grams, and the third one is 8.671 grams. Okay, so we already know that that's not very accurate. The reason we know it's accurate, or it's not accurate, sorry, is that the real value, the accepted value, is 5.670. Okay, so we are not accurate at all. But these values are all very close to each other, so we would say that they're very precise. So they're not accurate, but they're very precise. Okay? Now on the other hand, you could have measurements which are not very precise, but they're accurate. Okay, so for example, if the accepted value is 5.670, you could measure 5.7 grams or 5.6 grams, and that would be pretty accurate because that's, that's fairly close. It's just those aren't as close to each other, so they're not very precise. Another way to think about this is archery. Okay, in the archery example is you're trying to hit the bullseye, and the bullseye is the accepted value. Okay, so if you have a bunch of shots that are all in one corner that are real close to each other, those are precise but not accurate. Okay? Likewise, if you have shots that kind of cluster around the accepted, these are accurate, but they're not very close to each other, so they're not precise. And if we wanted something that was accurate and precise, they would have to be close to each other, and they would have to be close to the accepted value. So these would be accurate and precise. Okay, and the final thing that we want to talk about right now is the fact that this precision is related to the number of sig figs. And finally, we can talk about the uncertainty of the data. Okay, so the uncertainty of the data is equal to the range of values divided by 2. So as an example, let's say I go back to my 3 precision measurements. Okay, so I have 8.673, 8.672, and 8.671. Okay, if I look at the range of that data, the largest is 8.673. Okay, so that's the max. The minimum is 8.671, and so the difference between that, or the range, is the max minus the min divided by 2. So 8.673 minus 8.671 over 2 is very small. So that's 0.002 divided by 2, which is 0.001. Okay? So obviously if I take the average of these 3, the average value is right in the middle, 8.672. But then the uncertainty, 0.001, gets added on at the end. Okay, so this is how you do it if you measure something multiple times. If you only have one measurement, it's a little bit different, and we'll talk about that in a little bit later video.